Chapter 8, Storing Lists of Values. That's not the real beginning of Chapter 8. Chapter 8, Common Collections. Rust's standard library includes a number of very useful data structures called collections. Most other data types represent one specific value, but collections can contain multiple values. Unlike the built-in array and tuple types, the data these collections point to is stored in the heap. I know it says on the heap, but I like saying on the stack and in the heap. It means the amount of data does not need to be known at compile time and can grow or shrink as the program runs. Each kind of collection has different capabilities and costs, and choosing an appropriate collection for your current situation is a skill you will develop over time. In this chapter, we'll discuss 3 collections that are used very often in Rust programs: vectors, strings, and hash maps. A vector allows you to store a variable number of values next to each other. A string is a collection of characters. We've mentioned the string type previously, but in this chapter we'll talk about it in depth. A hash map allows you to associate a value with a particular key. It's a particular implementation of the more general data structure called a map. To learn about the other kinds of collections provided by the standard library, see the documentation, cough cough RTFM. We'll discuss how to create and update vectors, strings, and hash maps, as well as what makes each special. Storing lists of values with vectors. The first collection type we will look at is vect, also known as a vector. Vectors allow you to store more than one value in a single data structure that puts all the values next to each other in memory. Vectors can only store values of the same type. They are useful when you have a list of items, such as the lines of text in a file or the prices of items in a shopping cart. Creating a new vector. To create a new empty vector, we can call the vecNew function, as shown in listing 8.1. Let v vec of I32s equal vec new Note that we added a type annotation here. Because we aren't inserting any values into this vector, Rust doesn't know what kind of elements we intend to store. This is an important point. Vectors are implemented using generics. We'll cover how to use generics with your own types in Chapter 10. For now, know that the vect type provided by the standard library can hold any type, and when a specific vector holds a specific type, the type is specified within angle brackets. In listing 8.1, we've told Rust that the vect in V will hold elements of the I32 type. In more realistic code, Rust can often infer the type of value you want to store once you insert values, so you rarely need to do this type annotation. It's more common to create a vect that has initial values, and Rust provides the vec macro for convenience. the macro will create a new vector that holds the values you give it. Listing 8.2 creates a new vec I32 that holds the values 1, 2, and 3. Okay, so we will call this use the macro. Okay, function use the macro. And here we are. Let viv. Every time they make me make a new vector, I'm going to add another v. Now this is happening. Vec bam. I mean bang. That's not it. There it is. Uno, dos, three. Because we've given initial I32 values, Rust can imply that the type of v is vec I32, and the type annotation isn't necessary. Next, we will look at how to modify a vector. Updating a vector. To create a vector and then add elements to it, we can use the push method, as shown in listing 8.3. Okie doke. So this will go here. We will say v dot push. Let's push a 5, 6, 7, 8. Okay, and then yankety yank, plop plop. And I don't know how to do the fancy, multiple cursor business. I guess I'll probably. Why you say? What's this? What is this? What's the squiggle? It's gonna say, let me show you what you can do. Oh, change it to mute. It's funny because this light bulb most of the time is like, look, okay, here's the answer. Just delete this line. You don't know what you're doing. Just get rid of it. But no, okay. Mute. Got it. Thank you, light bulb. Let mute v vec I32, and then we're pushing 5, 6, 7, 8. As with any variable, if we want to be able to change its value, we need to make it mutable using the mute keyword, the mut keyword, as discussed in chapter 3. The numbers we placed inside are all of type I32, and Rust implies this from the data. So we don't need the vec I32 annotation. Dropping a vector drops its elements. Like any other struct, so vectors are structs. Okay? A vector is freed when it goes out of scope. Listing 8.4. Okay. Goes out of scope, and then alright, so we've got use vec, use the macro, okay, and well, I mean, yeah, so I can't use the vector VV. I mean, can I? No, this is what they're telling me. Print line. I'm gonna do that, and then it's colon hashbang, and then comma, Vivi. I don't understand. Why are you complaining? I gave you so many symbols. Okay. And it's gonna, I want it to, let's see. Have I actually accomplished getting it to tell me that it's out of scope? No, well, one thing I see is that, that's the hotkey doesn't work. Okay. I'm gonna need one of them's. How many squiggles does that? Oh, there's a problem. Thank you, squiggles. That goes there, and that is garbage. Okay, what now? Oh yeah, oh that's right. It's supposed to be a question mark. Can I have, what? What? Squiggles, what? Oh yeah, we knew that. Car, go, run, yes it do. No, not in there. There's no okay. When the vector gets dropped, all of its contents are also dropped. Meaning those integers it holds will be cleaned up. This may seem like a straightforward point, but it can get a bit more complicated when you start to introduce references to the elements of the vector. Let's tackle that next. Reading elements of vectors. Now that you know how to create, update, and destroy vectors, knowing how to read their contents is a good next step. There are two ways to reference a value stored in a vector. In the examples, we've annotated, and on that note, let me come over here and get rid of this. That right there. Annotated, where was I? In the examples, we've annotated the types of the values that are returned from these functions for extra clarity. So there are two ways to reference values stored in a vector, and here we have annotated the types of the values that are returned from these functions for extra clarity. All right, it's time to let, should I just go back into use the macro? I probably should. Okay, so we'll let VV vec 1, 2, 3, 4, 5, let third be a reference to an I32. So vector slice, because that's sort of what a string slice looks like. It's a reference to stir. Okay, and we'll put a 2 in here, right? And then print there we are. I'm gonna want a new line. All right. The third element is, oh, come on. Is that, okay. Well, you know, go. Here we are. Third. Right? Match. Oh, we're putting in a match statement. All right. Match get to, sorry, I should say get, so as not to conflate it with the version control system we all love. Third, wrong arrow. Let me read some stuff while I'm working on this. So note two details here. First, we use the index value of 2 to get the third element. Vectors are indexed by number starting at 0. Second, the two ways to get the third element are by using a reference and square brackets, or by using ampersand and square brackets, which gives us a reference, or by using the get method with the index passed as an argument, which gives us option reference to t. Yeah, I'm gonna have to listen to this to get that. So here we are, some third, and it looks a lot like this. So that's not what I meant to do. There we go. Print third element is third, but in this case, since it is a match expression, we want a comma. It is a match expression, yes. So no semicolons allowed. Keep your semicolons to yourself. None. None of that. Yeah. So I'm using print instead of print line just because I kind of want to experience the difference. So we're going to print. Nope. And then a comma. And let's run it. Did they? Wait a minute now. I see some red over there. I see Ferris with his claws up in the air. Yeah, they got me. Oh wait, just kidding. Nope, that's my bad. My bad. Sorry, just kidding. Right. Any more of those? Yep, just one right there. So, all right, Control T and cargo run. The third element is 3. The third element is 3. Because I used print. Okay, so this is the thing that I stop and talk about in every video. All right, so I used a new line at the beginning of print, which is, excuse me, kind of the it's the using the print macro instead of print line with a new line at the beginning of the slice is the supplement. It is the complement. It is some other math word to print line because print line puts that new line at the end. And I see now that I forgot to put the new line here in the none arm. So let's see if we can get that to happen. I think that would be here. And I can replace this with a 5. And so there is no index 5 in this vector because it starts counting 0, 1, 2, 3, 4. Wait, 0, 1, 2, 3, 4. Yes, if we want that, then that is at index 4. So now when we run this, it should give us, well, you know what it will do is, wait a minute, hold on now. This is going to be, it's going to give me a runtime error. So let's just is big ol' nope. Oh. Here we are. Yeah, that should fix it. Cargo run. Oh. Oh, okay, I get it. So the problem is that we tried to let third here. Yeah. That's where the error came from, I think. There we are. The third element is a big ol' nope. The third element is 3. What? Oh, so many things to change. Why I gotta change all the things? Okay. This will definitely work. Guaranteed. It did. Okay, so I didn't give the new line at the beginning or the end. So if you want me to stop talking about new lines, put it in the comments, and I might ignore you. So I do want a space after nope. Oh, space before nope. And I do want a new line after nope. So let's make this a print line. Print len. Okay. For the fun. We did it. The third element is a big old nope. Nope. Moving on. Rust has 2 ways to reference an element, so you can choose how the program behaves when you try to use an index value that the vector doesn't have an element for which the vector doesn't have an element. Just kidding. As an example, let's see what a program will do if it has a vector that holds 5 elements and then tries to access an element at index 100. As shown in listing 8.6, that's kind of what I just did by accident. Let's read and see if maybe I don't have to do that again. When we run this code, the first... Okay, I'm tired of not knowing what to call things. That. Table B10 shows the context in which square brackets are used. The context, square brackets with 3 dots, is an array literal. Okay, I'm going to use logic. Here we go. If you have x per semicolon len, array literal containing len copies of x per, type semicolon len, array literal, array type, collection indexing. Okay, I think this is what it is. Expression, collection indexing. Indexing. It's an indexer. Okay, I'm satisfied. So we note the 2 details. First we use, wrong spot. Correct spot. When we run this code, the first indexer method will cause the program to panic because it references a non-existent element. This method is best used when you want your program to crash if there's an attempt to access an element past the end of the vector. When the get method is passed an index that is outside the vector, it returns none without panicking. You would use this method if accessing an element beyond the range of the vector happens sometimes under normal circumstances. Your code will then have logic to handle having either some reference to element or none, as discussed in Chapter 6. For example, the index could be coming from a person entering a number. If they accidentally enter a number that's too large and the program gets a none value, you could tell the user how many items are in the current vector and then give them another chance to enter a valid value. That would be more user-friendly than crashing the program due to a typo. When the program has a valid reference, The borrow checker enforces the ownership and borrowing rules covered in Chapter 4 to ensure this reference and any other references to the contents of the vector remain valid. Recall the rule that states you can't have mutable and immutable references in the same scope. That rule applies in listing 8.7, where we hold an immutable reference to the first element in a vector and try to add an element to the end, which won't work. We've got let mut v equal the vec macro, and then let first, and then it's only got 0. It's really hard to count one number and see another one. 0, 1, 2, 3, 4. It only goes up to index 4, and then let first equal index 0. Well, that's fine. Okay, now we're using the push macro to push 6, but it only goes up to index 4. No, that's not the problem. The problem is that it's mutable, okay, and then we're taking a reference, that's the problem, a reference to index 0 and then trying to push back into the vector. Compiling this code will result in this error. Cannot borrow v as mutable because it is also borrowed as immutable. Yes. The code in listing 8.7 might look like it should work. Why should a reference to the first element care about what changes at the end of the vector? This error is due to the way vectors work. Adding a new element onto the end of the vector might require allocating new memory and copying the old elements to the new space if there isn't enough room to put all the elements next to each other where the vector currently is. In that case, the reference to the first element will be pointing to deallocated memory, and the borrowing rules say no. Yeah, okay, so vector is in the heap, and it's been allocated its spot in the heap, but it's growable, right? And so if it grows and it outgrows the spot that was allocated to it, then Rust will move it to a different place in the heap. And then any reference to an item in the vector that is pointing to where it used to be in the heap will be a dangler, I think. Okay. For more information, for more on the implementation details of the vect type, see the Rustonomicon. Iterating over the values in a vector. If we want to access each element in a vector in turn, we can iterate through all the elements rather than use indices to access one at a time. Listing 8.8 shows how to use a for loop to get immutable references to each element in a vector of i32s and print them. Let's do it. And I think it's time for a new function. So function use that macro. Okay. And we'll do this and that. Let v equal vec macro. You hear my coffee pot? Let v equal vec macro. We got a 100 and a 32 and a 57. These are i32s. I guess it just makes them i32s. Must be the default integer. Okay, so for I in reference to v println I. Okay, and then we got this and that and this. I hate how it breaks down there. So like it'll double up everything for me until there. No, won't. I can probably change that. All right, I, and looking good. Oh, gotta use that macro. Nope. Use that macro. Will do. Alright, and now cargo run. We can also iterate over mutable references to each element in a mutable vector in order to make changes to all the elements. The for loop in listing A9 will add 50 to each element. Okay. So now we're gonna let mutv well, I did something. Okay. Let mutv equal that, and then for I in reference to mutv, we will say there's a star there. Star. Dereference? Is that it? Is that the dereference? Or the... I don't know. Guess they'll tell me what that symbol is. We're gonna... Oh, wow. Okay. I expect I'm about to learn something. To change the value that the mutable reference refers to, we have to use the dereference operator, star, to get the value in I before we can use the plus equals operator. We'll talk more about the dereference operator in following the pointer to the value with the dereference operator. Whoa. Okay, so they're assuming I know what the plus equals operator is. I mean, I think I've seen this in shell, like, you know, you want to add something to a path, and so, like, hold on. Let me see if I can find an instance. Never mind. Okay. Using an enum to store multiple types. At the beginning of this chapter, we said that vectors can only store values that are the same type. This can be inconvenient. There are definitely use cases for needing to store a list of items of different types. Fortunately, the variants of an enum are defined under the same enum type, so when we need to store elements of a different type in a vector, we can define and use an enum. For example, say we want to get values from a row in a spreadsheet in which some of the columns in the row contain integers, some floating point numbers, and some strings. We can define an enum whose variants will hold the different value types, and then all the enum variants will be considered the same type. Boom. That of the enum. Then we can create a vector that holds that enum, and so ultimately secretly holds different types. We've demonstrated this in listing 810. They have an enum spreadsheet cell with 3 variants, an int, a float, and a text, 3 different types. Then they say let row equal vec macro. Oh, I already forgot what you call this thing. Ooh, my power just blinked out. But I'm on a laptop. Happy 4th of July, everyone. It's storming. Spreadsheet cell. Yeah, okay, and let me try to move through this fast. So we have a vector called row, and it's got spreadsheet cells in it, but they are different types because they're variants of the enum spreadsheet cell. Oh, I'm at the bottom. Rust needs to know what types will be in the vector at compile time so it knows exactly how much memory in the heap will be needed to store each element. A secondary advantage is that we can be explicit about what types are allowed in this vector. If Rust allowed a vector to hold any type, there would be a chance that one or more of the types would cause errors with the operations performed on the elements of the vector. Using an enum plus a match expression means that Rust will ensure at compile time that every possible case is handled, like in Chapter 6. When you are writing a program, if you don't know the exhaustive set of types the program will get at runtime to store in a vector, the enum technique won't work. Instead, you can use a trait object. We will look at that in Chapter 17. Now that we've discussed some of the most common ways to use vectors, be sure to review the API documentation for all the many useful methods defined on vect by the standard library. For example, in addition to push, a pop method removes and returns the last element. Let's move on to the next collection type, string.